NanoHub U, online instruction.
Hey everyone, welcome to lecture 3.4. So now we're actually going to talk about, since we've established the 3D finite difference timing method, specific implementation in MEEP, which is FTTT solver. So the first thing I should say before moving on is just something about stability. So we can perform what's called von Neumann stability analysis, and that allows us to actually decide if a standard problem would have a bounded and finite error that wouldn't expand rapidly or exponentially as optical waves, basically electric and magnetic fields coupled together, propagate through the system in finite difference timing. And so we can actually use the von Neumann stability analysis to derive the Courant condition, which is shown here. And so the Courant condition tells us that the time difference, delta t, that's being used in the simulation should be less than a certain value, which depends on both the speed of light and the spacing in the x, y, and z directions. So if we assume all the spacings x, y, and z are the same, and we write it as delta x, then that reduces to c should be less than 1 over root 3 times delta x over delta t. So if we choose that delta x and delta t are equal to 1, then oftentimes that gives us that c would be less than 1 over root 3. But in order to avoid being right on the edge of stability, oftentimes we choose c equals 1/2. And so this is, of course, in specific units for the simulation. It's not intended to directly be interpreted as a physical value of c. Okay. So then, anyway, so what is the key special features of the implementation of finite difference time domain in MEEP? Okay, so there are a number of actual features that are of interest. One is that you can perform calculations with arbitrary dimensionality, so you can do 1D, 2D, or 3D. And you can impose a wide range of boundary conditions, which may be the same in all directions or could be different and mixed, even in the same dimension in some cases. And then second thing is you have these so-called perfectly matched layers. Perfectly matched layers allow you to absorb light as it leaves the edge of the system, but make sure that doesn't go back in. So this is very helpful to reduce spurious reflections. And the third feature that's something we haven't really talked about before, but I'll explain in a few minutes, is called subpixel averaging, which is intended to improve the accuracy of the results for a given computational effort and discretization. Fourth feature is that there are features supporting symmetry and parallelization. So you can basically identify that two halves of the problem are identical or should map to one another either through mirror plane or rotational symmetry, and then you can cut down on your computational size. And then you can also do parallelization, which is very helpful if you have a large system and you need to split it across many processors. It's fully programmable, so it's basically linked in with a programming language called Scheme, which is based on Lisp, which I'll talk about a little bit later. And then it also implements nonlinear saturable gain media and frequency domain solver in case you need that. So the perfectly matched layers that I mentioned earlier basically suppress back reflection, but you can actually look at the degree to which they can suppress back reflection when they're on the edges as a function of the length of the absorber region. And so here it's labeled, you can see as like L, so it's basically the shaded region here. And so if you have a linear perfectly matched layer progression of both the electric and magnetic conductivity as you move away from the edge of free space, then you can see that actually making the absorber length longer helps because it becomes more adiabatic. So in other words, you have a more gradual increase in the conductivity as you go away from air into the perfectly matched layer region. And so the overall scaling goes like 1 over L to the 6th. So you can see that once you get to an L value with respect to lambda on the order of 100, then the back reflection is really, really small, like on the order of 10 to the minus 12 or so. But then if you have a quadratic or even cubic relationship, it's even better. So in fact, it can be as low as like maybe 10 to the minus 28 or so. So it's very, very low. And then this is actually discussed explicitly in this paper in Computer Physics Communications. And then another feature that's very helpful for this kind of system is subpixel averaging. And basically, this is an example showing like what is the value of subpixel averaging. So of course, I told you that before the resolution should go as like 1 over delta squared. The errors should also drop very rapidly. And so if you look at just these lines here, okay, so this is the linear error as a function of resolution in dotted line. And then the steeper slope here, which is in black, is the quadratic. So we want quadratic, but you can see that some of these methods that are more naive actually are just going like the 1 over resolution. So that's not really ideal. But then if we implement MEEP, then you can see that it actually comes very close to this 1 over delta x squared type scaling, which is very helpful. And then for the symmetry and parallelization features that I mentioned earlier, so this is just showing that if you had, say, an S structure with perfect symmetry, then you can basically use C2 rotational symmetry to split this into 2 halves, one of which is the region that's actually computed and stored, and then the shaded region is actually not stored. But if you try to plot the fields, the program basically recognizes based on the symmetry what the field should look like. So you can still plot the fields for the whole region. You don't have to manually infer those. And then another feature about splitting up into parallel regions, also discussed in this paper, shows that you can have multiple chunks, and then the chunks actually would recognize for each of its neighbors, like, is this owned by the same chunk or is it owned by a different chunk? And then each chunk can be mapped to a different processor, and it would automatically trigger inter-processor or inter-node communication, as the case may be, through something like MPI, message passing interface. And so then in terms of how it's fully programmable, obviously I have more detail later, but just to briefly summarize, there are all these different commands that you can use that will basically set up your system and allow you to set the geometry of the system, set the geometry of the dielectric, set the resolution, and then run it. In conclusion, MEEP has a lot of valuable features, and we'll explore them in more detail in the next lecture.